When it comes to looking at functions, what we have to be able to do is calculate key points of interest that exist on functions themselves and determine what they tell us about the actual equation and about the graph of the equation if we were to look at that. Now we're going to look at a few of these today, and we're going to determine how we can get characteristics of those set points and how we're able to then work with them in order to be able to sketch and start to build up an idea of sketching curves. So what we're going to focus on is critical points called extrema. And what these are is these are special points on the curve that we have to take into account when we're examining in sketching. So there's 9 different types of thing we have to look out for. So let's imagine we've got a point A, which is in the domain f of x. It's just a generic point, but we're able to calculate f of x of it. What we have to do is the first key thing is we have to remember that where f dash of a equals 0 or doesn't exist, these are called critical points. Now if you think back to when we did this previously, if f dash of x was equal to 0, that meant it was a stationary point. So technically, those are called critical points. But in this case, critical points do not necessarily always mean stationary points. They can mean other things as well. So we're going to look at that too. Now a function has a local minimum at some point A if f of a is less than or equal to f of x for all x in that region centred at A. So what that means, if you imagine looking at a sketch of that one, if I take my point being there of A, I can calculate f of a at that point and get a value. Any value around that I take for x in the region immediately around the point, if I take f of x, what you'll notice is that any of those values will be higher than the value of f of a. So what that means is that f of a there at that point is a minimum. So it's a local minimum in that little region. Same logic, but the flipping the sign the other way around is that it's a local maximum if f of a is bigger or equal to f of x in that region. So again, imagine turning it that way. There's my point A. If I did f of a, I'd get the value in the height there. But if I looked at any of the values around there, and I did f of x of any of those, they would all be less than that value. So it's a local maximum. Now we're calling it local because it's local to that region. There may be more than one maximum or minimum throughout the curve. We can't say it is the biggest or smallest point on that curve until we've done all of our calculations. And if it's not on the entire curve, the biggest or smallest, it's local to the area, so we call it local maximum or minimum. Fourth thing we have to look at is local extreme values, so the maxima and minima, as we've just mentioned here, these occur at critical points. So these occur at points where f dash of a equals 0, or it doesn't exist, there is no derivative at that point. The next thing we then have to look at is the end value, so the end point values of the function within the region we are in. Now the function has an end point minimum at a if f of a is less than or equal to f of x for all x in that region close to a. So let's imagine I've got a curve here. There is my end point of it. So there's my a. The curve exists all the way through here. Now imagine the curve has some sort of behaviour that does that. That there is the lowest value at that point in our area. So that there is an endpoint minimum. Similar logic for an endpoint maximum, the only difference is that f of a is bigger than or equal to f of x for all x in that region close to a. So again, it would be the same logic, the difference being the curve could look something like that, and it's the maximum in that region. And again, this point here, number 7, is that the endpoints are critical points. At those points, f dash of a equals 0 or it doesn't exist. So they are critical points. The last two look at maxima and minima, but look at what's called global maxima and global minima. Now we mentioned earlier locals, so within that region or throughout the area that we are looking at, but the function has a global maxima or a global minima if it follows these same rules here, but it's for all x in the domain of f. So at the point A, if f of a is less than or equal to f of x for every single x within the domain of f, it is called the global minima. Similarly, if f of a is bigger than or equal to every single value of f of x for the x in the domain of f, it is called the global maximum because there's no other point bigger than it within that region. So we have to remember the difference between that local and global. Global throughout the whole thing, local at an immediate point there. So let me show you an example of what I mean. Let's imagine I've got this function here and I want to identify the extrema, and key points of the function f of x equals magnitude of 3 plus 2x minus x squared in the domain 0 to 4. Now, first thing to look at is this part here, the domain. Written like this with the square brackets and the curly brackets, what that means and can be translated to is 0 is less than or equal to x less than 4. So it doesn't include the value of 4. So bear that in mind. Square bracket means it includes that value. Non-square bracket, it doesn't include that value. So I have to look at the extrema and key points of that. Now there are several key points and critical points within the graph. That one there at 0, 3, that is a critical point. That is where we start the function. The next one is at 1, 4. So 1, 4 is also a critical point because it's some sort of maxima. We need to determine what. This here is also another critical point at 3, 0. The reason being, the graph turns on itself at that point. So we need to look at the behaviour in that region. Now we could also say that 4, 5 is a critical point. You know, it's the end point of the curve. We could look at that, but we can't actually include it in our calculation because looking at the domain, it doesn't include 4 as being a value for x. Now, one thing to look at is if you look at the different points on the curve, this here is going to be some sort of maximum. The value on each side approaches it using the same values to get there. The derivative is going to exist at that point, so we're able to calculate and determine what kind of point it is. At this point here at 3 in y, and this point here in 3 in the x, the derivative does not exist for those functions, purely because it's discontinuous, i.e. the values don't continue on. So what we need to then do is look at these key points here. So first thing to do is actually take the derivative. So f dashed of x equals the magnitude of 2 take away 2x. Now if we look at 0, 3, we know that that's an end point, and of the two endpoints it's a minimum, so we know that that one there is an end point minimum. So we know at 0, 3 we've got an end point minimum. If we look at the point 1, 4 here, function is totally continuous through there, so what we then look at is f dashed of 1. F dashed of 1 is 2 take away 2x, so it's 2 take away 2 times 1, which is 0, so magnitude of 0 is equal to 0. What that then means there is that it's a local maximum point. Yeah. Derivative equal to 0, we're able to calculate that it's a turning point and it's a local maximum. At 3, 0, again, the derivative does not exist, so at this point, it's a local minimum. We know that it's a local minimum because it's there, and it's at the bottom of the curve. What we then have to do is look at the final key point of interest here. Now we could say that this one here is an end point maximum at 4, 5. It's the highest point overall, and it's the end point of the curve. However, again, the same logic as before, we're not including the 4 in it. So we cannot say that 4, 5 is an end point maximum. We can't say it. Simple as that. What we then have to do is look at each of the bits of the function and see exactly what we have here. Now this key point here at 3, 0, that is the smallest point overall in the entire graph. So we're then able to say, we've said it's a local minimum, but actually, upon reflection, we know that 3, 0 is actually a global minimum. Now, we're looking for the maximum, and again, 4, 5, which would be an endpoint maximum, would have been a global maximum had it been included. But because it's not, we're not able to determine that it is the maximum point of our whole curve, so we actually don't have a global maximum for this one because it's not included within the domain of the function we are looking at. So the function in this case has no global maximum. These are the kind of things you have to think about when you're looking at it. I know it can seem a bit complex and a bit of a pain sometimes, but we have to think about all these different factors. Looking at curvature of curves is actually something that's quite important as well, but it all depends on orientation. Imagine you were looking at this curve up here from either of these two sides of orientation. If you were looking from the left into the curve itself, it would look like it's curling away from you, so you would think to yourself, well, it's a concave curve. However, if you were on the right hand side staring at it, it would be curving towards you, so you would think it was a convex curve, i.e. it's coming towards you. What we have to do is we have to use this in order to be able to then look at the gradient of a curve and determine whether it's a minimum or a maximum dependent on that. So what we're going to do is we're going to look at the concavity. Now if you look at this graph here, if you look at the curve between A and B, you'll notice that the gradient is getting steeper and it's increasing at this point. If you look from B to C, you'll notice it's sloping down, so you would say the gradient is decreasing at that point. At point B, it becomes almost completely vertical for a minor split seconds, and then it changes. So it goes from increasing to decreasing at that point there. What we're going to do is look at this and how we can calculate this and determine if it's concave up, like this bit here, or concave down. And the way that we do that is we look at the second derivative of a curve. Now we know that the derivative, f dash of x, measures the rate of change of a function. Now we can relate this to several properties of maths, including speed and velocity, optimization, and the gradient of a line. Now the second derivative measures the rate of change of the rate of change, i.e. the rate of change of the gradient itself. So this is going to be used to tell us if the slope is increasing in terms of gradient or decreasing. Now what we can do is we can use this in place of a nature table. Now I know we've looked at maximum and minimum at higher, and we've used a nature table to determine the behaviour around it and whether it's a maximum or minimum point. But actually this makes our life a lot easier. If we calculate the second derivative and it's greater than 0, gradient is increasing, curve is concave up, so it's a minimum. If we calculate the second derivative and it's negative, gradient is decreasing, it's concave down, so the point is a maximum. So one calculation using this set of rules here allows us to determine the nature of the turning point straight away. Let's imagine I give you the curve y equals 4 plus 7x minus 3x squared, and I say to you, what is the nature of the turning points of that curve? Well, we know to calculate the turning points, we take the derivative and set it equal to 0. So let's do that first. So let's do dy by dx and set it equal to 0, and in this case we know derivative dy by dx is 7 take away 6x. We set that equal to 0 in order to get the turning points. Solving this, we get that x is equal to 7 over 6. So I know the value of the turning point in terms of x is 7 over 6. What I then do is I want to determine the nature, and in order to do that, I take the second derivative and I then look at the values of it. So if I then do d2y by dx squared, so that's my second derivative of it, 7 would go to nothing. I would then end up with negative 6. Now this has ended up being quite nice because I've got a negative second derivative. So what that means is at that point, my gradient is decreasing, so I'm ending up getting a maximum turning point. And this is what you'd expect. If you look at this curve here and the equation of it, it's a negative x squared. So you'd actually expect the curve to do something in terms of that. You would expect it to look in that format there. So you'd want a maximum turning point. Well, in this case, I've got a maximum turning point. Using the second derivative, we can do it in one step, rather than mucking about with a table of values and a nature table in order to be able to do the same calculation we've just done. Remember that second derivative helps determine the nature of the turning points, and it makes our life a whole lot easier and helps us look at the concavity of the curve itself.